Okay, let's start with a pretty wild idea. What if the fundamental rules that run our entire cosmos, the actual laws of physics, aren't set in stone? What if, over billions and billions of years, they've been slowly, kind of subtly, changing? It's a radical thought for sure, and one that really challenges everything we think we know about cosmology. So, to really get why that idea is such a game changer, we first have to talk about the biggest puzzle in all of physics. I like to call it the 95% cosmic mystery. And it's pretty simple, really. We have absolutely no idea what most of our universe is made of. Just look at this chart. This is our best map of, well, everything. And you see that tiny little sliver up top, the 5%? That's all the normal stuff. Every star, every planet, all the gas and dust, you, me, everything we've ever seen. The rest of it, that huge, massive chunk labeled dark energy and dark matter, is a total mystery. It's the great cosmic unknown. All right, but here's the twist. The theory we're digging into today asks a really mind-bending question. What if that 95% isn't made of some mysterious stuff at all? What if it's just an illusion? An illusion created because we've misunderstood the rules of the universe all along. For decades, these two ideas have been our go-to explanation for that missing 95%. You've got dark matter, which is supposed to be this invisible cosmic glue holding galaxies together with its gravity, and then you have dark energy, this strange force that's pushing the entire universe apart faster and faster. They're basically the two pillars holding up our standard model of the cosmos. And look, there's a really good reason scientists believe in them. These ideas just seem to perfectly explain some of the biggest things we see out there, like why galaxies are spinning so fast they should be flying apart, or why light from distant objects gets bent when it passes by huge galaxy clusters. And of course, why the whole universe seems to be expanding at an accelerating rate. The evidence, well, it seems to fit perfectly. So you're probably thinking, if the standard model works so well, why mess with it? Well, there's a radical new idea coming out of the University of Ottawa that says maybe we should throw out dark matter and dark energy completely and replace them with something way more fundamental. So this is the core of it right here. Professor Rajendra Gupta isn't trying to add new, invisible stuff to the universe. Instead, he's suggesting that the cosmic recipe itself is changing. What if the fundamental forces of nature have actually been getting a little bit weaker as the universe gets older and expands? So how on earth could one single, elegant idea solve both of these massive mysteries at the same time? It seems almost too good to be true, right? Well, let's take a look at how one new law could explain two totally different cosmic puzzles. It all boils down to this concept of evolving constants. Now, we're all taught that things like the strength of gravity are, well, constant. They're fixed numbers that never ever change. But this theory says, nope. It suggests they're actually dynamic, and they've been evolving right along with the universe itself. And this is where it gets really clever. The theory says this one change has two different effects. On a smaller, galactic scale, where you have a lot of stars and gas bunched together, these weakening forces actually make gravity appear stronger over vast distances. It holds the galaxy together, just like we thought dark matter did. But then, on the massive cosmic scale, across all that empty space between galaxies, that same exact principle creates a gentle little push outwards. It mimics dark energy perfectly. So you see, one law, two totally different effects. Pretty neat? Now, if you start messing with the fundamental rules of the universe, you're not just changing what's in it, you're changing its entire history. And this theory has a huge impact on the cosmic timeline. This is the number we all know and love, right? 13.8 billion years. It's the currently accepted age of our universe, based on that standard model. It's really the bedrock of modern cosmology. But if those fundamental forces have been getting weaker over time, then all our calculations about how fast the universe has been expanding are wrong. According to Gupta's model, the universe could be nearly twice as old, a staggering 26.7 billion years. And a longer timeline like this could actually solve another big headache for astronomers. You see, with the standard model, scientists have been totally baffled by these huge, mature-looking galaxies that seem to pop up way too early in the universe's history. But if you look at Gupta's model on this timeline, giving the universe an extra 13 billion years or so, well, that provides a lot more breathing room for these cosmic giants to form and grow up naturally. Okay, but let's be real for a second. An idea this revolutionary, well, it needs some seriously revolutionary evidence. So, how does this new theory actually stack up against the reigning champion of cosmology? This is basically the trial by fire for any new theory. The standard model, we call it Lambda-CDM, has been tested against decades of incredibly precise data. Think of it like the heavyweight champion of the world. Any new challenger doesn't just have to be good. It has to be as good as, or even better than the champ at explaining everything we see. And to be honest, recent evidence is still coming in on the side of the standard model. For example, a big study looked at how stars move around in these tiny, faint dwarf galaxies. And what they found was that computer simulations that included dark matter predicted their movements perfectly. The other models, the ones that tried to modify gravity, they just couldn't match what we actually see. That's a huge point for the champ. This table really sums up where we're at right now. You can see that for the big picture stuff, like why galaxies rotate the way they do or why the universe is expanding, both models have an answer. One uses dark matter and dark energy, the other uses evolving constants. But when you zoom in on the nitty-gritty details, like the movement inside those dwarf galaxies, the standard model is a perfect fit with the data we have. Gupta's model, well, it still has to prove it can do that. The really good news, though, is that we might not have to wait forever to find out who's right. We have these amazing, powerful new observatories coming online, like the Euclid Space Telescope and the Vera Rubin Observatory, and they are going to collect exactly the kind of super detailed data we need to finally settle this debate, one way or the other. So, what's the big takeaway from all of this? I mean, whether the laws of the universe are actually changing or not, this whole debate tells us something really important about how science works. And this is a point I really want to drive home. Even if Gupta's model ends up being completely wrong, it's still incredibly valuable. You see, bold, challenging ideas like this are what push science forward. They force everyone to go back and recheck their most fundamental beliefs. Real progress doesn't come from everybody just agreeing all the time. It comes from these brave new ideas that really challenge the way we think. And that kind of leaves us with one last really deep thought to chew on. Are we living in a cosmos that's run by a fixed, eternal set of laws that were locked in at the Big Bang? Or is the rulebook for the entire universe still being written, evolving, and changing right along with space and time? The answer is still out there, just waiting for us to find it.